In part 1, we have discussed the orthogonality property of the recursive polynomial. So now let's discuss another property, that is the recursive property. This polynomial will satisfy a recursive relation, that is L dash n t minus L dash n minus 1t plus L n minus 1t is equal to 0. So now let's get the value of L1 of t by using this expression. We know L0 of t is equal to 1. Put n is equal to 1 in the first expression. L1 dash t minus L dash 0 t plus L dash 0 t is equal to 0. Now putting the values of L0 of t in this expression, we get this is equal to 0. Now L1 dash t is equal to minus 1. L1 of t, integrating both sides, we get minus of t plus v. Now as we know that the value of L1 of t will be 1 minus t, so previous observation. So this equation will satisfy that. So that's what we get from the recursive relation. Now there is another way by which we can get the value of these recursive polynomials, that is by using the generating function. The generating function which we get for recursive polynomials, it will be summation k is equal to 0 to n minus 1 raised to power n minus 1 raised to power k, n factorial into t raised to power k upon k square into n minus k. Now this is L n of t. Now let's get the value of n is equal to 0 by using this generating function. We get L0 of t is equal to summation k is equal to 0 to 0, and k get only one value, that is equal to 0. So we put just k is equal to 0 in this expression. Minus 1 raised to 0 is 1, and 0 factorial is also 1. T raised to power k is equal to 1 divided by 0 factorial square, which is also 1, and 0 factorial, which is 1. So we will get L0 of t is equal to 1, which will satisfy our previous observation. So this is all about Hermite and recursive polynomials. Let's move to our third topic, that is the moment of inertia matrix. Of inertia as we know that inertia is the ability of a body to resist the change in the motion in it. Mathematical expression is derived is as follows. Let there is a point of mass m and the axis of rotation is this one, and the perpendicular distance of this point mass from this axis of rotation, let's say it is r. So the I, that is moment of inertia, is equal to m into r. Now when we are talking about a continuous body, we should like a continuous body, and this is our axis of rotation. What we will do is we will separate the body into point masses, each having a mass equal to dm, and then the moment, and we will write the moment of inertia of the whole body as a summation of dm into r, where dm is the mass corresponding to each point mass and r is the corresponding distance from the axis of rotation. Now talking about angular momentum. Angular momentum is equal to moment of inertia multiply angular velocity. Now let's assume we have a 3D body and this is our axis, that is x, y, and z axis. And now we want our 3D body to rotate about these three axes. So the angular velocity which we get is through the expression hx, hy, hz is equal to ixx minus ixy minus ixz minus yx yz minus ixy minus y. W of x, W of y into W of z. Now the matrix which we get here, this matrix is known as the moment of inertia matrix. In this matrix, the Ixx is equal to dm, which is the point mass of the 3D body, into y square plus z square, okay, integration. And similarly, Iyy is dm into x square plus z square, and Izz is equal to dm into x square plus y square. And about Ixy, here Ixy is equal to dm multiplied by x into y. This is Ixy. Similarly, we will get I of yx is equal to dm into yx, and Ixz which is equal to dm into xz, and so on. And putting these values, we will get the angular momentum along the x-axis, along y-axis, and along the z-axis. Now let's discuss the properties of this inertial matrix. As we know that Ixy is equal to integration over mass dm into x into y, and I of yx is equal to integration dm into y into x. Now we know that these two values are equal. So talking about our moment of inertia matrix, which we discussed previously, which is Ixx minus Ixy minus Ixz minus Iyx plus Iyy Iyz minus Izx minus Izy Izz. Now in this expression we get this is equal to this. Similarly, if we will see, this expression is equal to this and this is equal to this. So we can say that the moment of inertia matrix, it is a symmetric matrix. That is, this, if we will call it as I, then I is equal to I cross. This is our first property of moment of inertia matrix. Now moving to our second property. If we will see, there are special type of axes that are known as the principal axis. In these type of axes, what is the case? That the moment of inertia matrix which we get is a diagonal matrix. What we mean by diagonal matrix is that all the elements which are not diagonal, they are zero. So we can say that a matrix is said to be diagonal if all the elements other than these diagonal elements, they are zero. That is, so if around any axis, if we will get the moment of inertia matrix in this form, we can say that the